All right, folks. Well, welcome back. I want to go ahead and continue on with where we left off with yesterday, and just I want to go over with you the a few questions from the um, Poggle activity yesterday. So if you don't have it in front of you, please make sure you check your answers with what we're going to go over right now, and then come by if you have any questions. Come by and see me after school today about that Poggle activity. So please make sure you get that done. And again, like I said, if you have any questions about it, come by and see me. But if you want to go ahead and pause the video at this point, go get the Poggle activity and then have it in front of you, and then that way then you can go ahead and follow along with what we're going to do here in lecture. Okay, so like I said, I'm going to go over a few questions from the Poggle activity here to help us understand the nature of the balanced equation. We saw then yesterday with the balanced equation that it gives us information. We can use the balanced equation as kind of a set of instructions that we can use to carry out the chemical reaction. Okay? And so we need to be able to interpret the balanced equation in terms of what the reactants are and what the products are. And we learned that back in chapter 11 when we talked about when we wrote out these equations. And so we use the symbols there. We use the symbols for the reactants. We use the symbols for the products. And so the symbols then will either tell us that the reactants are elements or compounds and what they are. So the symbols help us to identify what the reactants are and what the products will be. And then the balanced equation also has a set of numbers, the coefficients that go along with those symbols, that go along with those formulas. And those coefficients tell us how much of the reactants and how much of the products we expect to be a part of that reaction. Okay, so we have to be able to interpret these chemical equations. Okay, and if we're going to use them as a set of instructions, we need to know what those numbers mean. We need to know what the formulas mean. And so with that said, then we were able to describe then what those numbers mean in terms of the atoms, the total number of atoms that are involved in the chemical reaction. We saw then that in a balanced equation, the number of atoms that we start out with and the types of atoms that we start out with in the reactant side has to be exactly the same as the number of atoms and the types of atoms that we end up with on the product side. So the number of atoms have to be equal. And we can obtain that information from the balanced equation, okay, by just looking at the atoms, the symbols for the atoms that are involved, and counting them up and keeping track of those atoms. Okay? Then we were able to see then that we can use the balanced equation to describe then the total molecules, types of molecules, and how many of them are involved. And remember, we use that term molecule very generically, but to just describe then the types of compounds and the types of substances that are involved, okay? The types and also the numbers. And so we were able to take those numbers, the coefficients, and describe then the types of compounds, the types of reactants that were involved in the beginning on the reactant side, and the types and the number of compounds and the substances that we obtain on the product side. And so that's the information that we can get from the balanced equation. But the issue with that, we left off with this yesterday, and the issue with that then is that when we carry out a chemical reaction, we typically don't carry out the chemical reactions with single atoms or atoms. We don't carry out the reaction with single molecules or multiple molecules. We have to carry it out with quite a few molecules. Okay, and when I say quite a few, how many? We need a whole lot being, say, Avogadro's number of molecules. Okay? And so remember what we had then with Avogadro's number, and Avogadro's number, and we learned this back in chapter 10, so make sure you review that. Okay. Avogadro's number then represents this many particles, 6.02 times 10 to the 23rd. Avogadro's number is a very, very big number, and that corresponded to, and make sure you remember this, 1 mole. Okay, so if we can interpret the equation, interpret the quantities, the number of particles in terms of the mole unit, then we have now a whole lot more that we can work with. Okay? And so we can use the coefficients then to get that information, because the coefficients then also correspond to the mole. So we want to be able to obtain the number of moles. And so what the nice thing about the balanced equation then is that the coefficients also indicate the number of moles, how many moles of each reactant, how many moles of each product are involved in the chemical reaction. And when we do that, we are working on a scale now that is much bigger, and we can use this relationship here in order to obtain more information about the reaction. Okay? Specifically, in using this relationship here and what we know about the mole and its relationship to, say, mass, okay, and what we learned about the relationship of the mole to volume, specifically of a gas at STP, we can now also obtain information from the balance equation, and not directly, but indirectly, the information about the mass and volume, which is essentially what we need to actually carry out the reaction, because we can't measure out moles, we can't measure out atoms, we can't measure out individual molecules, but we can measure out mass and we can measure out volume. And so the goal then in stoichiometry is to be able to obtain information about mass and volume of reactants and products in a chemical reaction, and so that we can go ahead and weigh out or to measure out these masses, these volumes, in order to carry out the reaction itself. Okay, and so that's the goal. And let's go ahead then and let's take a look at how we get to that point. Okay, all right. Let's go ahead then, and what I'd like to do is let's go ahead. Let's talk about what these mole ratios are. Okay, so mole ratios are basically the ratios of moles of the reactants or the products. So essentially, we're comparing the ratio. We're setting up a comparison between two different parts of a chemical reaction. Okay, and it could be, you could be comparing the reactants. You can be comparing reactants to products. You can be comparing the products. But a ratio is just a comparison. We're basically comparing quantities. Okay? And so when we have the mole ratio, what we're doing is we're comparing the moles of the components of reaction to each other. Okay? And so that's what I want to get to here. And so let's go ahead, and I want to do a couple of problems here with you. So let's go ahead and let's do the first one. So again, if you have the your POGO lab in front of you, let's go ahead and do this. Okay, so we're considering then this reaction again that we've been considering quite a bit. So this is the ammonia, the formation of ammonia from nitrogen and hydrogen. Okay, one nitrogen combined together with 3 hydrogens to form then 2 ammonias. We can also interpret this in terms of 2 nitrogen atoms combined together with 6 hydrogen atoms to form 2 nitrogen atoms and 6 hydrogen atoms as well. Okay, so that's how we can use the coefficients. Okay. But what are the coefficients each of the substances here? So let's go ahead and write this in. So we have then, it's understood to be 1 here. Okay, so it's 1 here, we have 3 here, and then 2 here. Okay, so those are the coefficients that we have. So essentially then, and instead of drawing the particle models, instead of drawing the particles, I'm going to write out for you what we had yesterday, the Lewis stat structure. So therefore then we have 1 of these molecules, okay? And we're going to combine it together with 3 of these particles, okay? And that's what this is telling us. And that forms for us 2 of these particles here. And that is the representation of this reaction. Okay, so 1 nitrogen, 3 hydrogens, and to form 2 ammonias. And if you notice here, let's just count atoms really quickly again. We have 2 atoms of nitrogen on this side, 2 atoms of nitrogen on this side. We have 6 atoms of hydrogen on this side. We have 6 atoms of hydrogen on this side. We have 1 nitrogen molecule on the left-hand side and 3 hydrogen molecules on the right left-hand side, and we have 2 molecules of ammonia on the right-hand side. Okay, all right. So that's what we have there with the how we can imagine what this is. So and again, if you want to draw the particle model, you can imagine one of these particles here breaking up, and it's forming combining together with 3 of these here, okay, to give you 2 of these particles. So these bonds have to break, and I like drawing the Lewis stat structure. You can actually see the bonds that break. This 1 triple bond has to break. These 3 single bonds have to break to form these 3 single bonds and these 3 single bonds. Okay. All right. Let's go ahead then. Let's take a look at number 2. Okay. In number 2, then we're going to calculate for the amounts of each reaction. So they describe for us in each one of these boxes and each one of these rows here. They describe for us the amounts that we have to deal with. Okay. And so with that said, then we want to be able to calculate for that and then come up with the ratio here. And we're going to reduce the ratio, come up with the ratio here that describes the ratio between nitrogen, hydrogen, and ammonia when we increase it. So remember, here we have only one molecule of nitrogen, 3 molecules of hydrogen, and then 2 molecules of ammonia being formed. Okay, so in this first reaction here, in this first part here, they tell us that if you run a reaction, okay, if you run a single reaction, how many molecules of each substance we form? Okay, so if you run this reaction once, okay, you're going to form then one molecule. I'm sorry, you're going to use 1 molecule of nitrogen. You're going to use 3 molecules. Oh, sorry. You're going to use 3 molecules. Okay, 3 molecules of hydrogen to form then 2 molecules of ammonia, which gives us a simplified ratio of 1 to 3 to 2. Okay, so that's the ratio there. Okay, all right. Let's take a look at the second situation, the second reaction. Okay, this time we're going to run the reaction, but then we're going to run it 100 times. Okay, we're going to run it 100 times. Then, if we run it 100 times, then we need then to start out with 100 molecules of nitrogen. We need, if we run this correctly, if the reaction occurred 100 times, okay, then 100 times, then you'll need 300. Okay, of those, okay, and you will form then 200 molecules of nitrogen. So essentially then what we're saying here then is that we take the same reaction, instead of running it once, we run it 100 times. If we run it 100 times, we need a whole lot more nitrogen, a whole lot more hydrogen, and we're going to form a whole lot more ammonia. Okay, and so if we write out the ratio here, it's going to be then 100 to 300 to 200, though. So instead of just 132, we will now need 100. So we're going to run this 100 times. We're going to need 100 molecules of nitrogen. We're going to need 300 molecules of hydrogen to form 200 molecules of ammonia. But if we reduce this again, it's going to be 1 to 3 to 2. We still have the exact same reduced ratio. Okay. All right. Well, let's consider this then. Okay. Instead of running it 100 times, okay, instead of running it 100 times, okay, instead of running it just once in a single reaction, instead of running it 100 times, let's say then we run it 538 times, which means then we need 538 times more. So this is going to be 538 times more nitrogen molecules that we need to start out with. Okay. If you do the math here, you're going to multiply 3 times 538, and you will need then 1,614 molecules of hydrogen to start out with. And if you take 538 molecules of nitrogen and react it with 1,614 molecules of hydrogen, you're going to form then 1,076 molecules of ammonia. So instead of running it once, instead of running this reaction once, instead of running it 100 times, we're going to run it 538 times. It's some random number that they threw out there. Okay? The ratio then is going to be, and if we do this, then the ratio is going to be 538 to 1,614 to 1,076, which again, reduced down to its simplest whole number ratio, it's going to be 1 to 3 to 2. Okay? The ratio stays the same. And if you notice here, folks, each one of these simplified ratios ends up being the ratio of these coefficients here. If you take the ratios of these coefficients here, it is a 1 to 3 to 2 ratio. So all of these here, the ratios here all end up being exactly the same as the ratio from the balanced equation. Okay. And so that's going to be something that you want to keep in mind. That's going to be important as we move forward. Okay, so let's continue on then. Okay. And let's take a look at what we have. Okay, so let's continue on. Okay, and let's do number 4 here. Okay, so we typically don't run a reaction with just 1 molecule of nitrogen, 3 molecules of hydrogen, or individual molecules. We typically don't run the reaction with 100 molecules of hydrogen, nitrogen, 100 molecules of 300 molecules of hydrogen, produce 200 molecules. We don't even run it with 538 molecules of nitrogen and 1,614 molecules of hydrogen to produce 1,076 molecules of ammonia. those numbers are still way too small, folks. It is nearly impossible to get to isolate 538 molecules of nitrogen and 1,614 molecules of hydrogen, let alone trying to isolate one molecule of nitrogen and 3 molecules of hydrogen. Okay, so what we can do then is we scale it up. Okay, so this time though, instead of running it one time, okay, let's say then that we're going to run this reaction 1.602 times 10 to the 23rd times. That's how many times we're going to run it. It's going to take you till the end of eternity for the most part to run it that many times. But instead of running it that many times, then, okay, let's say then we start out with this many. So if we're going to run it that many times, we're going to start out then with 6.02 times 10 to the 23rd molecules of nitrogen. Okay, we're going to start out with, and again, what we're doing is we're just taking this number here, and remember what we did in the previous table, and multiplied it by the coefficient, which is going to be, and I'll write here again, we had 1, 3, 2. Remember we had that. Okay? And so we're going to triple this number here, which is going to give us 1.81. And so go ahead and put that up a little bit. Okay, it's going to give us a amount of 1.81 times 10 to the 24th here. Okay, and then we're going to form then 1.20 times 10 to the 24th here. Okay, all right. So that's how many molecules will form. If we run this reaction, okay, this many times, okay, this is how much we'll need. This is how many ammonia, nitrogen molecules we'll need. This is how many hydrogen molecules we'll need. And this is how many ammonia molecules we will form. And so again, folks, you don't want to sit there and run this reaction this many times. Okay? Again, it'll take you until the end, pretty much till the end of eternity in order to get this done. Okay? And so that takes a long time. So instead of running it this many times, what if we started out with this many particles and run it once? We just run it once, and we start out with this many particles of nitrogen, this many particles of hydrogen. We will form this many particles of ammonia. And if we take the ratio of each one of these and we reduce it, and so basically what we do is to reduce it, we take each one of these numbers here and divide it by this, we're going to get then a 1 to 3 to 2 ratio. Okay, all right. So if you understand this, and you understood what I just said here, so we don't want to run it, we don't want to run this reaction this many times, but we want to start out with this many particles. Make sure you understand that this many particles here represents 1 mole. That is going to be 1 mole, this particle here, okay? This then represents, and so make sure you're able to do that conversion, okay? This represents then 3 moles of hydrogen, and this represents 2 moles of ammonia, which gives us a ratio then of 1 to 3 to 2 again. But this is what we call the mole ratio. Why? Because we are comparing the amounts of each one of these, each one of the reactants products in terms of the unit mole. Okay, in terms of the unit mole. Okay, and so this is then what we refer to as the mole ratio. Okay, the ratio obtained. So make sure you understand then the mole ratio we obtained then from this one then is going to be, and I wrote it here for you already. The mole ratio is going to be 1 mole of ammonia, nitrogen, to 3 moles of hydrogen, to 2 moles of ammonia, and that is our mole ratio. Okay, and again, why do we call this the mole ratio? Why is it called the mole ratio? Because we are comparing the quantities of reactants and products in units, in unit of moles. And that's why we call it the mole ratio. Which indicates then, and make sure you understand that, which indicates then what we're doing is we are using this many particles to describe the relationship between those. Okay? All right, very good. So with that said, let's go ahead and hopefully we have then the mole ratio. Okay, so we can interpret then let's go ahead and do this. We can interpret this reaction then in terms of the mole ratio, just like we did above. And so let's go ahead and finish this out here then. So then we start out with 1 mole of nitrogen. We have then 3 moles of hydrogen, okay, to give us 2 moles of ammonia. And again, if you add this all up, we have 4 total moles on the left. We only have 2 total moles on the right. And if you notice here, they do not equal. So there is no conservation of moles in this case. Okay. All right. Let's go ahead then and let's go ahead and let's do number 7. Okay, now that we know that, let's take a look at number 7. Okay, so I'm running out of time here. Let's go ahead then. What I'd like to do is I want to pick up with this problem tomorrow. But what essentially they're asking you to do in this one, folks, is that we know then that if we have, and for example, and I'll just write that here, we have 1 mole of nitrogen, for example, we know then that we would form 2 moles of ammonia. Okay. So if we start out with 1 mole, and that's what we have, that's what we saw on the previous slide, if we start out with 1 mole of nitrogen, we should get 2 moles. It is equal, we will get 2 moles of ammonia. Okay. The question then is, what if you change the amount here? Okay. Now let's say then, or change the amount here. The question then is, let's say if you only had half a mole of nitrogen, and I think you can do this in your head, how many moles of ammonia would form? Well, if you only have half of what you start out with, you should only get half. You should only have half of that. Okay. And so the question is, how do we get from here to here? Okay. And how do we get from here to here? Okay. This we get directly from the balance equation. This we get from our conversion. Okay, so tomorrow, what I would like to do with this particular problem then is talk about how we can do the conversions, and that, folks, is the first step in doing stoichiometry. This here, folks, is the first step in doing stoichiometry and understanding what it is. And so we will use this then. And so hold on to this. For tonight, then make sure you finish up this particular POGIL activity if you haven't gotten it done yet, so we can use this to talk about the first step in doing stoichiometry tomorrow, okay, which is comparing mole ratios here. And so make sure you get that done, and tomorrow we'll pick up with this discussion. Okay. All right, folks, very good. And I will come by and see me if you have any questions, okay, and I will see you tomorrow.